So I want to talk about these diagrams and arrows that François was drawing, but I know it caused some sort of panic in some people. So I want to give you some concrete examples of that and what they are, the vertices and arrows there, and how the group acts. So that's the goal of the talk. So it should be called configuration spaces. And the subtitle would be homemade vector bundles. Just for you. Just for you. We're doing this, constructing this one. And so this is like a not so major technical point, but I'm also happy with it because we were working with these spaces with no nice coordinates for like a year, and now we have like a really nice vector bundle stuff here. We'll make it to that in a fine way, mostly most of the time, and that's nice. So let's do the easiest example, or at least we can play with. Don't get anything else. Which is the following: you take space X, which are, maybe I should know which are 30. So have pairs of independent lines in Marquis. You could also do this for splitting into two subspaces. And the projection just gives you the second one. So this is a really, really basic example. And the only thing I'm going to say with a bit more special notation that will generalize is the obvious thing that any subspace complementary to X2 is the graph of some linear map. That's the only thing I know. But I want to say it in a special way that will work for these other things. So what is it? It's X1, X2. The dimensions are 1. And X1 plus X2 is our 2. Okay. You can imagine doing this with different dimensions, D1 and D2. And then there's a projection onto X prime, which is just a projected space. Okay. And the projection, so X is a pair. You keep the second one. And the goal, obviously, this is a really easy example. That's why I'm starting with this. So the goal is to turn this into a vector bundle. Turn it into a homemade vector bundle. With nice, that's what we are action. So the obvious thing to do is given X2 with fiber over X2 will be, you just need one angle, right? So it would be natural that the fiber would be just like the interval minus pi or something. Okay. And if now I turn it into a vector bundle, the fiber will be R. And I'm distorting the distance here. If I put a norm on this vector bundle, I'm distorting the distance, but it's locally bilateral. And for dimension theory, you don't care about locally bilateral. So I have the right to distort this interval of angles to come to a real line. So I can do. What do? You do the following. Take this will be like overkill the first one. what generalizes, we take V1 to two subspaces. And the properties that you want are that it's splitting. And in this case, this particular case, I want the only condition I have is that I want the second subspace to be split at fine. And I want to parameterize the fiber over X5. And then I'm going to take a space of linear mappings that go from R2 to itself. Linear. And the nice property is that V1 will go to V2, will go to 0 when I play it. So it's nil, there are nil. Where is it? Then I'm going to get the coordinates I want. My V will go from nil V to the fiber. That's right. And how does it work? It's the graph of the linear mapping between V1 and V2. What the metric said. So how do you write that? You do identity plus F V1, comma, and I could write, and will write again, which is just that parameterizes the space of splitting project to X prime as some space of linear maps. This condition is linear, these conditions are linear, so I can take it. So one-dimensional space. This guy's a one-dimensional space. But you can imagine I can do the same in R3, and the splitting is into a one-dimensional plus a two-dimensional space. And now this guy actually has dimension V1 times V2 of them. V1 dimensional V2. Already you get some parameterization. These are the coordinates. And so what's the coordinates, but they depend on the choice of some compatible splitting, splitting compatible with this. And but you want to make it vector, you have to choose some of the coordinates. You do that this, and what you do is for the fiber one instruction. The chart for the fiber over X prime will be phi V with V equals X prime per. Just the most obvious splitting you could get. This gives you the local chart. And then the nice thing that happens, not that difficult to see. Oh, I should write. So when you have your X prime, then I have some other line. W1. Then I have you want to parameterize this guy? X with X1. And so what do you get? If you draw parallel lines to X prime, you look at this vector there. And you're searching for phi W inverse of phi V of F. So what's the map? How much do I have to add in the direction parallel to this point to this subspace to get x or this thing here is multiply it. Projection. When I write projection to V1, along the splitting V1 for the kernel as it's prime minus projection W1 plus I. That's what they control. This thing here, it is the order. We'll have the formula for change in formula. Very simple. So the nice thing about that so when you act with the linear mapping, well, what's going to happen is the following. Have your x prime here, x by g, you get to gx prime. Correct? And so if I take a compatible splitting components there, for example, I take first one. All right, it's not going to go to g of x1 line first. And it's not the same as g of x prime first. Right. Those are two different things. So what's easy to see is that if you have some f f that you're going to apply the components for this splitting here, you look at the image. If you do phi so g, I should write phi of g b, and then you apply g, and then you do phi. Okay. It's not that hard to see. Is that if you use the splitting that you use here for coordinates goes to the splitting that you use over there, then the action is just conjugate by g. Gf g minus 1. A linear map again. And so now you have to switch from the coordinates given by this splitting, gx prime, g of x prime first, to the actual coordinates that you're using with the orange splitting. And what you get is that psi gx prime inverse psi prime by g in the middle. You can get, this is the only entire program. I wrote a program to give you the formula for other models of this type, and you get combinations of projection and weird things. But this one is the only one which right in home. You just get this thing over there, which would be x prime perfect minus g of x prime perfect, not the same thing, plus g f g minus. So this is my formula for the fiber-wise action of the group G. And what is it? Well, it's an affine mapping of that. It involves adding something and doing something else. So this is the important point that we talk. That's what. Okay, so are there questions to this point? We're going to be doing more exotic examples of this type of question, but yeah. Well, if you so I'm saying that each if you pick one complementary subspace to its prime, all the others are graphs of linear maps from this one to its prime, and it's one map, one graph. One question. Wow. Took way longer than I thought to say. All right. So, and one thing that I'm not going to do is if you do a splitting of RB into B1 and B2 dimensional, you get exactly the same formats. Exactly the same. These are projections along with splitting. They're not one dimensional, but same format. So this is the exact same thing. Okay. So now let's do one more. Maybe start seeing what's going on. Okay. So the nice thing is, in terms of, I should say it just family. We're trying to study the measure given by the Oseledets splitting in this space. And down here, you have the measure given by the stable subspace of the Oseledets split. And the conditional measures are the stationary measure whose dimension you want to understand. And where does it live? It lives on a one-dimensional vector space over each base point. So really, you're studying the dimension of a measure, which is, and also the action of G is a fine. So you're studying the dimension of a measure, which is stationary for some affine action. So it's really not a huge leap to do that. So that another example. All right. So now we can do splittings over flags. The one I wanted to know. Bear with me for the notation. For these guys, just x1, x2, x3. They're all one-dimensional in R3. And x2 now the guy downstairs uses just flags in R3, but I'm going to use this notation. So the guy down here will be x prime, and we will have a one-dimensional subspace which I will call x prime to 3, and it will be included in two-dimensional subspace that we call x prime to 2. Okay, that's the notation I want to use down here. Call them whatever you want. And the projection. Okay, so this is a flag. This guy is one-dimensional. This guy is two-dimensional. Okay. And the picture looks like this. Oh, sorry, I didn't say what the projection. The projection is phi of x will be x3, x2 plus x. All right. So the picture goes like this. We draw some splitting. X1, x2, x3. And when you apply the projection, you get some flag. Which is this one. This is the plane. And this is the plane. Okay. And that's my fiber one. And so I want to do the same thing as before. And if it looks up, how does this work? It works like this. You want to put coordinates. What you have to do is you have to choose some splitting. Again, just the splitting. And it was going like over here. The conditions are that V2 plus V3 be x prime V3 and V3 is prime. That's a compatible splitting We'll get black. Okay. Someone might be thinking, why not just take it? It's the same thing, have one of those to have a point in the fiber. True in this case, but not in the other. And how do the coordinates work? The same as before. You take the nil, place of the mountains. The mappings from R3 to itself, linear mappings. And what actually will satisfy? B1 will go to the sum, B2 plus B. So the graph of some linear map from this one-dimensional footprint to the plane will give you any other one-dimensional space in general position of that plane. And then B2 will go to B3. Will go to linear maps from R3 to itself with those properties and the coordinates that you're giving. Well, first you should check the dimension of this space of mappings, right? You have the choice of a map from a one-dimensional space to a two-dimensional space. And then you have a choice of a map from a one-dimensional space to another one-dimensional space, 2 + 1 = 3. And that's the space, that's the dimension of the fibers for this production. So it's the same. And the definition is the same as before. The last one is just V3. Second one will be some line complementary to its prime 3 inside of this plane. And the first one will be some line complementary to the plane. Those are my coordinates. And again, if I do maybe I should say it. You can pick a preferred coordinate for each base point by making the splitting as perpendicular as possible. In this case, it's actually perpendicular. So how do you do that? You take phi as x prime, phi b, or d equals. So it will be x prime to 3 perp. It's the first subspace. The second one will be x prime to 3 intersected with the perp. X prime to 3. And the third one will be x prime. So it's just the most perpendicular splitting problem. More or less, I drew here. X3, you pick it. The perp inside of this plane, you pick it, and then the perp of the plane. And that's your preferred coordinates. So with those coordinates, it's a vector bundle. And to understand the action of SL3, you need to know what the change of coordinates is. So here I will just say that, okay, you can pretty much do the previous example for the line. You can consider like you're splitting into 1, 2, 1, 2. And then inside this plane, you do the previous example again. And so you will get some horrible formula. Which will be something like this. That's that phi W minus 1 phi D. So that should be. And then when you look inside of a plane, prime to 3, you get the same example before. So your formula is like this guy. Is the same as before. Plus F. You restrict to that plane. And then the last thing you need to know is what happens when you find W1. Again, now you can ignore everything except for the plane and do the same example as before again. And you get I G Y I W plus that. Okay. And then you add those up and you get a formula for the change of variables, and it's still a prime. It's the only thing I care about. All right. Maybe what I'm saying is that if you reason in the same way as the previous example, you'll get a formula for what happens inside the plane and a formula for what happens in the plane. And if you add them up, you get something that's terrible, but it's you have potential. And as a consequence, you get the formula for when you consider the coordinates over on one fiber and the corresponding to the system, and the coordinates on the image corresponding to the image of the system is exactly the same as before. It's just going to be direction using the formula. So again, if I were to put in here, so I'm just going to take the conclusion, the action of G. That's the these fiber-wise. I don't think it's worth it to write again the same things again, but you get the flavor of what it's like. It's the same as before. So now the perp splitting, this guy, this image is not the perp splitting for the image, but you try to change the coordinates and add a bunch of projections and things. Okay. So that's the point. This is the vector bundle. When I act with the matrix, 3 by 3 matrix, okay, the fiber over this flag. When I look at the coordinates on the image flag, the action is on a fine line. So studying the conditional measures for projection. If I look at the measure given by Oseledets splitting, I look at its projection down here. It's a measure to the stable flag. Studying these conditionals is studying some sort of stationary measure for some affine action, except that it's on a vector bundle instead of. Maybe this is a good time. Question. Half an hour doing projections. Okay. So now let's do the terrible diagrams. Which I like a lot. Like my favorite thing that showed up in the groups of these things are these configuration spaces. And I think that these configuration spaces, they should have several other applications independent. They're like a some geometric object just there. And it should have many applications, in my opinion. But okay. So what is the diagram that François was drawing? It's intermediate bundles. Oh, I have to draw this picture here. Maybe this will take up the rest of the time just to draw the picture. Okay, so what do you want to do? I'm going to draw. Let's try to make this nice. So we gave this example of space of splittings, x1, x2, x2, as a total space, and then downstairs space of flags, and we're calling this x3 and x2, 3 would be the sum of x2 and x3. Okay, we study this one. Which bundles are in between these two? Is the question. And so the reasoning went like this. At first, you say, okay, having a splitting given this flag is the same as having another flag which is in general position with this. So the line of the new flag will be x1, and the intersection of the plane with this plane will be x2. That's the total space is just the space of pairs of flags in general position. And so the fiber over one flag is just the set of flags in general position. And you could say, okay, I could take partial flags in general position with the given flag at the bottom. That will give me two other bundles. If I just have one line in general position with its flag, I will get, hopefully I drew this correctly. I will get, oh man, no. Okay, so if I just have a line in general position with that flag, I will get flag. So 1, 2. Right. That's a bundle corresponding to pick a line in general position with this flag. And that's if I pick a plane in general position with this flag, I will get. Okay. You get a plane, and your given flag that you had at the bottom is this. Maybe it's not that. So this is x3, this is x2, 3. And you only remembered x1, 2. And that's another bundle. And basically, it's the space of pairs of flag and plane in general position with the flag. Okay? It also gives you the intersection of the plane with the plane, which is, you can call x2 if you want. That's so here you have 3 bundles over the space of flags, which come from taking partial flags in general position with the flag you have to call. And you can do the same game. They all have fine. I will define. Is that all it is? Good question. And it turns out no, there's 3 more intermediate bundles here. And what do they on the weirdest one? So essentially, we were reading Frank's paper, trying to understand how it works. And the 2 ones that appear here are when you interpret what he does in this context, you get 2 more. But not enough to get the dimension that we wanted. And so there's this crazy new one. And it's not that crazy. Now that you have it, but the listing. This is x2. This is x2. This is x1. Okay. It projects to this flag because you can do the sum. So it's the configuration of subspaces. That's why we call them configuration. The points are a line in general position with a plane that contains another line. Okay. Perfect. Yeah. Oh, one comma 3. So the projection, yeah, that's a great question. The projection from this one to this one is to construct the plane x1 plus x3, and we call it x1 3 down. So that's projection. Okay. And then you get the 2 ones given by Feng. Not that ugly. Not that good at drawing is the problem. Not that the thing is so complicated. Something like this. These are x1, 3, 2. There's a line here. Okay. And there's one more, which is x3 plus. Okay. So these are all the ones we can think of. The intermediate bundle between weightings over flags, between that. And you have natural projections from each one of these. Have natural projections, which are whenever the thing has an indexes, which consists of several numbers, add up the corresponding thing up there. Okay. Right, that's the diagonal. Let's I guess. I like them a lot. I know not many people were liking them, but this is pretty much my favorite thing of the they exist. So the three of them, I should maybe say something, but make this like this thing. The three of them corresponding to partial flags, or four if you consider the trivial flag. You don't include them. Those four. When you go up in dimensions, there are only okay. There are two to the t minus one of those things. And the total amount of vector one of configuration spaces that we have is more than exponential lots. Lots and lots of exponential. And we need them to prove very different. So the fact that they exist and we have the vector one is neat, like sort of here for them. And, so who wants to ask the question now with the also I forgot to say what? Oh, still have time. Okay. Oh, it's okay. Okay, so what can we do in 10 minutes? Okay. So what am I saying? What? All right. So what's the segment of this thing? Each of these, same trick as we did before. Pick any two, and you have a bundle, and you can make the bundle a vector bundle, and the action of SL3 is affine on the pipe. You work out all these cases. It's the same sort of trick. I can do one maybe. I want to do one. It's not really. Maybe not. Okay. No, let's do it. Maybe I should write it. Let's do an example. So maybe let's do the most exotic. The most exotic what? You've got take X to be this one. All right. So how do I write it? When we have going to write X2 not included in X13, which includes X. And when there's only one sub-index, a one-dimensional subspace, if there's two of them, and you project, not two, maybe black. The projection, probably make it up. Right? So X3 is already there. And I want it's the one in the middle. Three projects by just forgetting this guy and keeping the sum. And just to give you a sense of what the flavor this thing has, the coordinates. So the coordinates, the properties of the splitting depend only on the base point. So it's the same as before. Just pick a splitting.
G2 plus G3. And G3 equals X5.
So this doesn't change from the other example we did, which was this one. You have the same splittings that you consider. But what changes is the definition of which matrix will serve as the domain for your coordinates. The mappings that will serve as the domain first are linear mappings. But instead of V1 going into V1 plus V3, it's not there. So V1 will go into V2. We'll go to V2. We'll go. And this is the domain of my coordinates. Okay. And the sanity check is what dimension does the space have? Well, you're picking one mapping from another. One plus one. So that thing has dimension 2. And it's the same dimension you check as the fibers of this projection. Because you have to pick a line inside this plane, right? That's the one-dimensional plane. And then you have to pick a plane that contains this line, another one. So at least in terms of dimension, things are working out well. And your coordinates will be what do I need? I need X2 will be the image of it will be not included in the image of 1 plus 2. So there, with this mapping from V1 to V2, I'm telling you how to move this direction of it. And then this guy includes identity plus that of V3, which is just that's what. So what changes from the previous example is just the domain. The mapping is apply. And what you're doing is like a bit fancier version of subspace complementary to this guy is a graph. That's what you're doing over and over again. Yes. So over there, it will go to the sun. And down here, it can only go to the beach. So there's a smaller dimensional domain for the chart. All right. More questions? So what happens is here, you obviously we work on every arrow on its own. We work out, and here you get again a fine action of SL3, and obviously I for all dimensions, these things will have a fine action. And in general, you get polynomial. Okay. Yes. Oh, yeah, sure. Also, we can discuss. But yeah, for sure. And so I don't know if I'm doing it. Is this the most lenient? Yeah. So I think okay. So that's the picture of the configuration spaces. I hope that the spaces themselves One more here. Let's answer the question now. Something I like a lot. And so now, what are we doing? Doing this exact dimension theorem. That François said I would prove a lot of things, and I rebelliously refused to prove any of the things he said I would prove. Okay. I think this is important. I hope I'm nice. Okay, so what happens? How does it play? Okay, so what happens is the following. So you have your new probability on and assume that when you make it the random with new, you multiply, you get three distinct levels. Type 1, type 2. Okay. So Oseledets random state. One. And its distribution, consider its distribution. Let's call this top place of splittings. So you have a measure up here, the total space of this fiber bond. And when you project it downstairs to the bottom, the projection. So up here you have your measure. What do we call it? And down here you have a measure, the projection. And so it's 0, I think that's 0. Use 0, which happens to be the you check this one. But I don't really care. It's the distribution of the stable flat. So new check is instead of measure when you measure set A in the matrices, you can measure mu of A inverse, all the inverse. And this is the distribution of the stable flag. New check. And so you have a measure up here, and you have all these projections. You can project your measure onto each of these intermediate integrations. And for each projection, you also have a disintegration. Anytime you have two spaces, a projection, and you have to push for a measure, you can disintegrate. Places are nice, these are really nice. And so you have your conditional measures for every each experiment. You get so the measure will be like mu x given x prime. Okay, for now. And so what we want to prove is that these conditionals for almost every point in the base space will be exact dimension. So the two claims are claims that talk about the following two claims. I guess I should say claims of the following. We show the theory to prove that that dimensional. Step one step for fibers of dimension one. Now the arrows I drew there. Whenever the fibers of dimension one, the dimension of mu dimension. With the formula for the dimension, which I'm now calling, I don't know. Step two is you have x prime double prime and the exponent the Reynolds length. This one is one step. The exponent, the action. Fibers to the bottom, and the bottom fibers. Contract less. Just say the action on the bottom fiber contracts less than on the top. To if this, then the dimension of that. So the dimension of these conditions plus the dimension of this one will be the dimension of these. Those are the two steps. And now, so why is there an exponent on the case of the fiber is one dimensional? Because it's an affine action on a vector bundle with one dimensional fiber. Okay? So the linear part is just a number. And you multiply these numbers at random, you take a log right by n, there's some exponent. And now, conclude in 2 minutes. Let's give an example of why this might have something to do with the differences of exponents. I'll just write what François wrote, and we'll explain one of these. So what are they? It's 1 minus 2. It's 1 minus 2. 2 minus 2. 1. 2 minus 2. I'm writing down what the exponents on these fibers of dimension 1 will be. So let's give one example. That'll be it. So you have x this one and x prime this one. And so what happens is when you look at your random sequence of matrices, you have at time 0, you have the flag E3, E2 plus and omega. Okay, so this is a random point in this space, and we're looking at its distribution. And now the fiber that you have is a distribution of E3 omega E2. So what happens when you apply the matrices? Let's go this way, we go either way. G minus 1 omega, G minus 1, G minus 2 omega, up to G minus n omega. That will take you from left to right. If you want to go right to left, you have to apply the inverses. What happens is you land on some flag here. It happens to be E3 sigma minus n, sigma is the shift map on the omega. E2 plus E3 sigma minus n. Omega. All right. And in the fiber, you land on the pair E3 sigma minus sigma omega. E2. So what happens is, what are the other points on the fiber over this flag? There are other choices of lines inside of the plane E2 plus E3. Okay. So the other points in the fiber are other choices of lines which happen to lie in the same plane. So Oseledets theorem tells you that this big matrix product on E3, the vectors change their norm by exponential n chi3. And on E2, they change their norm by exponential n chi2. So what happens when you apply a diagonal matrix in R2, when you apply it to a line which is independent from the pattern space? So it goes to the expanding one by which rate? So this is so any line, this angle is theta, call this guy x. This angle is theta. And what you get over here is an angle which is more or less exponential minus n chi2 minus chi3 times theta. Okay. So this reasoning is why the exponent of the actually fiber number, which is bigger number, which is is actually a difference of a solid. That's all. Thank you very much. Did I go over? Sorry. Oh, you mean down here? No, here it's just because I only, okay, that's maybe a point that I didn't make here. We only care about the measure of the distance integration. We don't care about the measure of space. Yeah, but okay, but, well, if you see, I stood up. I see what I did wrong, which is incorrect. I should write here that each measure, and here I should write this guy in the bottom, But we only, our theorem is only about the conditional measure, not about the measure on the total space. But at the end of the game, you get the measure on the total space. But it's only about conditions. So here you have an argument to show that whatever the bottom measure is, I don't care. Well, the condition was it's a one-dimensional thing, and the dimension is given by some formula. Some entropy divided by then if you keep adding, going up, as long as it's more contracting on the fibers than on the projections that you already had, they add up. Yeah, we just prove exact dimensionality of the disintegration of this projection. Okay, not of the actual measure on top, although in the end we do prove it. More questions? All right.